In this video, we're going to start Chapter 11. And Chapter 11 is on solutions. We have talked about solutions a few times. Remember, a solution is a type of homogeneous mixture. There are other types of homogeneous mixtures that we will talk about here shortly, a solution being just one type of homogeneous mixture. Remember when we were classifying matter at the beginning of the semester, right? We had two main types, pure substances and mixtures, right? Under pure substances, we had elements and compounds. And then under mixtures, we had homogeneous and heterogeneous. Remember that homogeneous mixtures were mixtures that don't look like a mixture, right? We would say that it has a constant composition. We would say the mixing is uniform. Right? Even though it's different things mixed together, each retaining its own chemical property, right? It's a mixture, not a pure substance. It looks like it's one thing. So it has a constant composition. Usually I would use Kool-Aid as my example, right? If I was to take Kool-Aid powder, sugar, and water, mix it all together, it doesn't look like there's three different things in there, right? It looks like one solution, right? It's a type of homogeneous mixture having a constant composition or being uniform. Right? Uniform might be a better way to say it. We had said that our solutions are made up of two components, a solute and our solvent. We can have more than one solute. So in my Kool-Aid example, I actually have two solutes, right? We could put an S after it here in parentheses. This was the component or components, if we have more than one, present in the smaller amount. So in my Kool-Aid example, both sugar and Kool-Aid powder would be solutes. And then my solvent is the component. We'll only ever have one solvent present in the larger amount. So water in my Kool-Aid example. And then you mix your solute with your solvent. That's my solution, right? Remember, a solution is a mixture of at least two different things, a solute and a solvent. Remember, we said we could form solutions from any states of matter, so it doesn't have to be a solid and a liquid. It could be two liquids, it could be two solids. Air is a mixture, right? It's a mixture of different gases. I could have a gas and a liquid, so soda, right? I have carbon dioxide and then, water if I just wanted soda water. We could mix solids and gases. Any types of states of matter can be combined to form a solution. So a type of homogeneous mixture, homogeneous meaning that it has a uniform composition made up of two different types of components, a solute, and I can have more than one of those, and then a solvent, we're only ever going to have one solvent. Solvent, the component I have most of, right? My solute or solutes, the components that I have less of. There are other types of homogeneous mixtures I had just mentioned. Solutions being the focus of this chapter, but I do want to mention two other types. So, solution. And then I'm going to have a colloid and a suspension, which I will write down in a minute. But kind of the difference between these, whether something is classified as a solution versus a colloid versus a suspension, is going to be the size of the particles. So of my three types, my solution, this is going to have the smallest particles. And when I say particles, we're generally talking about the solute particles. So the solute, we would say, is in the solvent. So the thing that's being suspended is going to be small. So these are going to have the smallest particles of the three types. They tend to be transparent or clear. Be really careful not to get clear and colorless mixed up. I can have a red solution that I can see through, right? If it's transparent, it means I can see through it. If I had a glass of Kool-Aid and I put my hand on the back side of that glass and looked through it, I could see my hand. So just because it has color, right, doesn't mean it's not clear. If it lacks color, then it's colorless. So just water. Water would be clear, right? It's transparent. It would also be colorless because it doesn't have color. So be really careful. when I say they tend to be clear, that doesn't mean they can't be colored. I can have a blue clear solution or a blue transparent solution. If I let solutions sit around for a while, the particles stay in solution. So the way we would say this is that it does not separate upon standing, right? If I was to make my Kool-Aid, which is a solution, mix it up, put it on the counter, go away, come back in 2 days, I'm not going to find a pile of Kool-Aid powder on the bottom of my glass, right? It's going to stay in solution. So solutions are going to have the smallest particles of my 3 types. They tend to be transparent or clear, can still be colored. And then if I let it sit around for a while, it's not going to separate. My second type is going to be a colloid. These are going to have medium-sized particles. And I could give you sizes for reference. It's all in like the picometer range. So like you don't need to memorize them, just in comparison to each other. I know medium and small is pretty vague. But I just want you to know that the size of the particles in a colloid are bigger than that of those in a solution, and then smaller than that of those in a suspension, which will be our third type. These tend to be opaque. So you can't see through it. Sometimes we'll say cloudy. And if you let it sit around, it does not separate. So it does not separate, just like our solution, upon standing. An example of this one would be milk. Right? Milk's not clear or transparent, right? It's opaque. And if you let it sit around for a while, and I'm not talking about it going bad, that would be a chemical reaction. I'm just talking about physically separating. So milk not, curdling or going bad. So just milk in its same state. If you let it sit around, you're not going to come back and find all the protein at the bottom. So milk has larger size particles. If I wanted to compare it to Kool-Aid, which I'm probably going to spell incorrectly. The sugar is a much smaller particle than the proteins that are in milk. So it tends to be transparent. Colloids tend to be opaque. Neither one separate upon standing. And then a suspension is my last type. And these have larger particles. So largest of the 3. And honestly, these ones kind of walk the line. They're not truly homogeneous. I don't think there's an E in truly. And the reason I'm going to say that is what I'm going to write down next is that they do separate upon standing. And remember, a homogeneous mixture is a mixture that doesn't look like a mixture, right? It's uniform in composition. But if you let this settle out, now it looks like a mixture, right? If you let it sit for a while, the two, the solute and the solvent are going to separate from each other, and it's not going to look homogeneous. So if you get it when it's all kind of stirred up in suspension, right, it looks like a homogeneous mixture. If you let it separate, it's not truly homogeneous anymore. So this does separate on standing. And just kind of an everyday example would be paint. If you've ever, painted a room and then, right, you open it up and you have like all of like the oily stuff on top and all the pigment at the bottom, and it has to be stirred up. Often at the store, they'll stir it for you. But then if you go to put a second coat on, right, you paint your walls and then you close it up and then you let it sit for a day and then you come back and it's all separated again. That's a suspension. So paint would be an example. On blood, if you take a sample of blood and let it sit for a while, the red blood cells are going to settle down to the bottom. The plasma will be at the top. So a suspension, blood is also one. So it does separate on standing. So 3 types of homogeneous mixtures: solutions, colloids, and suspensions. As I go down, my particle size is getting larger. Solutions do not separate, Neither do colloids if you let them sit around. A suspension does separate, so not truly homogeneous. Transparent when you look at it, and then opaque. Suspensions are also going to be opaque. Fit that in there somewhere, or cloudy. I had said a little bit ago that we could form solutions between any states of matter, right? It doesn't just have to be solid and a liquid. It could be a gas and a liquid, and so on. What I didn't mention is that not everything, however, right, can form a solution. So while solutions can form from any states of matter, not just anything can form a solution. So what I mean by that is if I was to take carbon tetrachloride, right, CCl4, and mix it with water, I'm actually not going to form a solution. I could form a mixture, but it would be heterogeneous. It would not be homogeneous. And remember, solutions are homogeneous mixtures. So I can make a mixture out of this. I cannot make a solution out of this. And the reason for this is the polarity. Carbon tetrachloride is a non-polar molecule. If we were to draw it out, I have carbon in the middle. I have 4 bonds to chlorine. All of those bonds are polar. It's just that they're arranged symmetrically. So they're all going to cancel each other out. And the molecule itself is going to be non-polar. Water is bent. It has 2 polar bonds, and because of its bent structure, those do not cancel each other out, right? There are 2 lone pairs on here. The 2 lone pairs aren't why it's polar, however. It has to do with the shape. The reason it's bent, though, are because of those 2 lone pairs, so they do actually contribute in that way. And if I was to try to take my non-polar carbon tetrachloride and combine it with my polar water, it's not going to be homogeneous. And you've probably heard this saying before, and it's like dissolves like. And what we mean by that is we need to have similar polarities. Essentially the intermolecular forces, because when I form a solution, I'm actually going to be forming intermolecular forces between the solute and the solvent, right? If it was a pure liquid, if I just had water, water would have intermolecular forces with water. If I had just carbon tetrachloride would have intermolecular forces with carbon tetrachloride, right? Just London dispersion forces because it's not polar. When I mix them together, what I need to do is break some of the intermolecular forces between the carbon tetrachloride molecules. I would need to break some of the intermolecular forces between the water molecules, and then I would need to form intermolecular forces between carbon tetrachloride and water. And that generally only happens if the types of intermolecular forces that they have are similar. For that to happen, their polarities would need to be similar. So kind of our saying, like dissolves like, is solutes and solvents with similar polarities. It's actually similar intermolecular forces, but those are similar when the polarities are similar, will form solutions. Again, remember, I can still form a mixture. Carbon tetrachloride and water will form a heterogeneous mixture, just not a solution. So if it's polar, it will form a solution with something else that's polar. If it's non-polar, it'll form a solution with something else that's non-polar. Polar and non-polar, in my example here, those would not form a solution. So kind of an example for us. Besides the one we already did, we could put that here, will not form a solution. So another one we could do, let's use carbon tetrachloride again. And NH4+. Actually, let's change that to NF4+, just for something different. So our question is, are they both polar? Are they both non-polar? If that's true, then yes, they will form a solution. That's our question. Will these form a solution? If our answer is no, then they will not. As far as are they the same? So will these form a solution? We already said that carbon tetrachloride was nonpolar. So our question, what is nitrogen tetrafluoride? And if you were to draw out the Lewis structure for this one, you would have nitrogen in the middle, 4 bonds to fluorine. Each of those fluorines have 3 lone pairs. I do have a formal charge on nitrogen. Because I have 4 bonds and no lone pairs, it's tetrahedral. Fluorine is more electronegative than nitrogen. So this one has a very similar situation as carbon tetrachloride in the fact that I have 4 bond dipoles, but they're arranged symmetrically, so they're going to cancel each other out, and we're going to say nonpolar. I do have a positive charge, but that's my formal charge. That's different than looking at bond polarity, so don't let that trip you up. So nonpolar and nonpolar, will these form a solution? Yes, because they have similar polarities. Same question above, these will not form a solution because one's nonpolar and one's polar. So a typical question I could ask, something like this. So it's taking the concepts that we used in chapter 10, right, determining what types of intermolecular forces they have and then applying it to can I form a solution out of them. For water, for ionic compounds are polar by nature. Right? They're made of ions. So instead of having a partial positive end and a partial negative end, I just have a full-blown positive and negative. So ionic compounds are polar. So if I was to take sodium chloride and ask if it would dissolve in, I don't know, C5H12, this is ionic, right? Sodium ions and chlorine ions, so it is polar. This is just carbon and hydrogen, so it's non-polar. So will sodium chloride dissolve in this is pentane? The answer is no, right? No solution formed. The one thing that you need to watch out with ionic compounds is water. Remember, water is polar, right? We just looked at it up above. It's bent. If it was linear, we would say nonpolar, but it's not. It has a bent structure, so water is polar. Not all ionic compounds do dissolve in water. So even though this is polar and this is also polar, you have to look at the solubility rules. So be careful for that one. If you have an ionic compound in water, then you need to look at your solubility rules. So use solubility rules, right? The ones that we did in chapter 7, right? On the back of our periodic table there. You to know this term, and solvation, or our ions are solvated. So solvation. And essentially what that means is that our solvent molecules are surrounding and stabilizing whatever it is that they're dissolving. I'm going to use sodium chloride and water as my example. So in this case, the solvent molecules, which will be water in my example. So the solvent molecules are going to surround and stabilize, in this case, the ions. Whatever it happens to be that you're solvating. So I'm going to be solvating sodium chloride. So that's what I'm going to be stabilizing. I just want you to be familiar with that word. It's going to come up a little bit in 152 and it comes up in organic. It's just one of those terms. If someone says it, I want you to know what it means. So our example, if I was to take sodium chloride and then I was to dissolve it in water, so I'm going to form an aqueous sodium chloride solution, right? If I didn't want to write in water, I could put an AQ after it. Remember that AQ means it's in water. This is one of those where I would have to make sure I check my solubility rules, right? If I have an ionic compound and I'm dissolving it in water, I need to use those solubility rules. And I know that sodium chloride is soluble in water. So what's going to happen is we're going to break the sodium chloride, right? Ionic bonds. There's an ionic bond between those. We're going to break some intermolecular forces between water molecules. And both of those changes are actually going to take energy to do that. This is going to have a positive enthalpy change, and then this is also going to have a positive enthalpy change, right? Anytime I break a bond, we have to put energy into doing that. So whether it's an ionic bond, a covalent bond, or intermolecular forces, if we're going to break that connection, it is going to take energy. What I'm going to do then is we're going to form intermolecular forces between the water and my ions. So we're going to solvate my ions. We're going to form, in this case, it's going to be an ion dipole force. Between the sodium and water, and between my chloride ions and water. And then that's going to have a stabilizing effect. So I'm going to have a negative enthalpy change for that. So we have to put energy into that part, but then we get energy out of it when we're done. And we're going to get more energy out of it because we're stabilizing it, right? Solvation is a stabilizing effect. I'm going to just draw water out here by itself, just to remind us that the oxygen is the partial negative end, right? It's more electronegative than the hydrogens are. So that's my partial positive. So when I take sodium, sodium is my cation, right? It has a positive charge. When I surround it, right, in my solvation here, we're going to surround it. When I surround it with my solvent molecules, I'm going to have it oriented so the oxygen is facing towards the sodium ions, right? The positively charged sodium is going to be attracted to the partial negative end of water. So I'm going to draw my water in this direction, and I'm literally going to surround it. So we would say it's solvated, right? I'm surrounding my ions with my solvent molecules. And then I can draw a dotted line to represent those ion dipole forces, right, between the sodium ion and the partial negative of water. When I draw a similar one for the chloride, chloride has a negative charge, so this time I'm going to orient my solvent molecules so the hydrogen is facing the chloride, right? The hydrogen is the partial positive. The partial positive end of water is going to be attracted to the negative chloride ions. And then you can do dotted lines for all of them or some of them, it doesn't matter. But it's going to be the attraction between the partial negative hydrogen, partial positive hydrogen, that makes no sense, and the negative chloride. Right here, it's between the positive sodium and the partial negative oxygen. So surrounding those ions, I would say that they're solvated.